SwayamPrabha. Digital India. Educated India.
Okay, welcome back. We were discussing energy analysis of closed systems. In this particular lecture, we would like to understand the first law of thermodynamics for closed system, that is fixed mass systems, and we will develop general energy balance applied to the closed systems. Further, we are going to take certain examples in order to apply the first law of thermodynamics for such a system. So let us try to revise what we have learned as far as energy balance is concerned. So this is a generalized form of energy balance where the net energy transfer by heat, work and mass to the system should be equal to the change in the internal energy, kinetic, potential and other forms of energy. So this is the energy balance for any system undergoing any process. Okay, so this is a generalized form of energy balance. You can write this expression in terms of rate form. So here is the rate of net energy transfer by heat, work and mass should be equal to the rate of change in the internal energy, kinetic energy, other energies of the particular systems. Now you can, if it is a rate is given to you, you can calculate the total quantities in terms of for a given change in time. So here for example the Q is nothing but Q dot, which is rate of heat transfer multiplied by delta T. That would be your interest in specific time range. And similarly you can obtain W, the work done, and as well as the total energy change of a system. So this is specifically for the energy balance per unit mass basis, and one can also write a differential form for this. So this is energy balance in differential form. So this we have already gone through in our earlier lectures, so we are trying to revise this in order to address some of the problems which we are going to undertake in this particular lecture. So we are aware of the fact that W net will be equal to Q net for a cyclic process. So this is a cyclic process and so it returns back here, so then hence in this case your delta E should be 0 and thus your W net out is same as Q net in. You can write in this form where W net out is nothing but the system work which it does on the surrounding minus the surrounding work which it does on the system, and similarly Q in minus Q out. So this basically, by putting the in and out as a subscript, we already have defined the sign of this Q and heat and as well as the work. So typical energy balance when sign conventions are to be used is basically heat and input and work output are going to be positive, or heat output and work input are going to be negative. So that would be our sign convention we are going to use it if the direction of the heat and work are not available for your given problem. So that means we are assuming in this case the Q net in with the heat supplied to the system and the work done by the system. So the Q minus W is nothing but delta E, or this can be a generalized expression for your first law for the closed system. So for a cyclic, as I said, delta E should be 0 and thus your net heat in should be same as net work out. Now from the perspective of first law, the heat and work are not distinguishable. So it's difficult to distinguish in terms of, because these are both related to the energy transfer dynamical form. But this becomes more relevant when we discuss the second law, and then we will realize the importance of distinguishing different type of dynamical transfer of energy into form of heat and work. And general energy balance is summarized in this here. Okay, just for a quick reference. So let us consider now an example for a constant pressure expansion and compression process. Okay, so what we have is a closed system. Okay, we are going to consider quasi-static equilibrium. We are going to consider a constant pressure process. Okay, we can start with our generalized energy balance or the first law of thermodynamics. E in minus E out is delta E system. Or in other words, we can say if the only energy transfer is in the form of heat and work, then you have the changes are given in the form of Q and W, and this we can write as U plus delta KE plus delta PE. Considering no change in kinetic energy and potential energy of the system, these two terms are going to be 0. Okay, what about work? So Q is a net heat provided in, or Q in. W we can write as sum of all possible work done by the system. So this could be the boundary work plus other set of work. Okay, could be electrical work or so forth. And then you have this Q. Okay, now which is nothing but U2 minus U1. Okay, now for a constant pressure, the boundary work, we know, we have done this exercise earlier, is nothing but P0, which is a constant, multiplied by the change in volume, V2 minus V1, and then you have this other work here. You can take this term and bring it here, and you can rewrite this expression as U2 plus P0 V2 minus U1 plus P0 V1. And we know this from our earlier exercise that this term, the internal energy plus PV term, we have identified, or rather represented this term as enthalpy. So this is going to be H2 minus H1. So this is the energy balance expression for the case of constant pressure expansion or compression of the system, and in this case your delta U plus boundary work is going to be change in enthalpy of the system. So this is only true for constant pressure expansion or compression, okay, process. So now let's make use of this analysis and solve certain set of problems. Okay, so we have a piston cylinder device which contains 25 gram of saturated water, and it's maintained at a constant pressure of 300 kilopascal. Resistance heater within the cylinder is turned on, which pass 0.2 ampere for 5 minutes from a 120 volt source. Okay, so there is a electrical work which is done on the system. At the same time, there is a heat loss of 3.7 kilojoules. So we have to find the final temperature of the system. So we'll start with the first law. So we can write as E in minus E out is delta E, or we can write it as delta U, because there is no change in kinetic energy or potential energy. So what would be E in and E out? So the energy being provided to the system is W electrical in, and what is E out? E out is the heat which is out from the system, okay, which is this, plus any boundary work done by the system on the surrounding. Thus we can write this expression. Now we can take this here, and we've already discussed about this constant pressure energy balance, where you can write, okay, the W B plus delta U as delta H. So this is nothing but W E in minus Q out equal to delta H. And what is WB here? Is going to be this pressure of 300 kilopascal multiplied by the change in volume. So we have this expression. Now we need to find out the WE in, which is nothing but the voltage is already given to you, the voltage multiplied by the current multiplied by the delta T, and this is going to be 120 volt, 0.2 ampere, 300 seconds, and then you can use the conversion of 1 kilojoules per second is 1000 volt ampere, okay, and this should be 7.2 kilojoules. So you can plug in here, and the final expression would be 7.2 kilojoules minus 3.7 kilojoules. What is delta H? We have to use some tables, so we will make use of appendix tables, There the values are given in terms of specific enthalpies. So this is rewrite delta H as m times H2 minus H1, where m is nothing but 0.025 kg times H2 minus H1. So we need to find from here this expression, we need to find H2. H1 we can make use of tables because we have all the information. Let us see how we do this exercise. So what is H1? H1 is, if you look at the state, be given the saturated, because it's a saturated water vapor at 300 kilopascals. So H1 is going to be gas of saturated vapor at 300 kilopascal. So let's look at the table. So table is given here. So this table is going to be saturated water pressure table, which is your A5. Okay. So here is a 300 kilopascal. The corresponding Hg is 2724.9. So we're going to write this as 2724.9. So we plug in this value in the previous expression, and from there we can, so from here we can get H2, okay, by plugging in this value of H1, okay, which is 2864.9 kilojoules per kg. Okay, so this is the value which we have now, okay, from the expression 2864.9 kilojoules per kg. Now the question is whether state 2 lies within the saturated water system or is it in a superheated range. So in order to find out the state, we compare H2 values with the Hg values at 300 kilopascal because the pressure is given constant. So the question is if this is greater than Hg or if this is less than Hg and greater than Hf. So let's look at 300 kilopascal again. So we know this 300 kilopascal, the value of Hg was 2724 and our value is greater than 2724. So that means H2 is greater than Hg at 300 kilopascal. This indicates superheated state. Okay. So now the next thing is we have to take a look at the table of superheated state. So this is your superheated state for the specific pressure 0.3 megapascal or 300 kilopascal, and for that we specifically obtain this value 2864.9, which is almost close to this value, and this corresponds to the temperature which is on the left side. It corresponds around 200 degrees Celsius. So that would be your temperature because this temperature corresponds to pressure 0.3 megapascal or 300 kilopascal and your H2 which is given to you 2864.9 kilojoules or approximately 2865 kilojoules per kg. Temperature based on this table is close to 200 degrees Celsius, which corresponds to this particular level. Okay, so this is the way to solve a typical problem based on the tables for the constant pressure system. We can take another example. This is an unrestrained expansion. So what we have here is a rigid tank which is divided into two equal parts by a partition which is here. Initially one side of the tank contains 5 kg of water. So the 5 kg water is here. The pressure is 200 kilopascal. Temperature is 25 degrees Celsius. And other region is evacuated, which means vacuum. Okay. So the partition is removed and the water expands in the entire tank. Water is allowed to exchange heat within its surrounding. So there is a heat exchange, okay, a heat transfer until the temperature in the tank returns to the original 25 degrees Celsius. So this is the final temperature. Initial temperature is also given. So what we need to find out the volume of the tank, final pressure and the heat transfer for this process. So let's first look at the volume. What is given to us is P initial, okay, which is 200 kilopascal, okay. And the first thing is to identify the initial state. So is it a saturated vapor liquid system or is it a compressed liquid or it is a superheated vapor? So let's first look at based on the knowledge of initial pressure and as well as the tables. So P initial is given and the temperature is given. What is the corresponding saturation pressure at 25 degrees Celsius? So this is your 25. We look at table A4. This is your 25 degrees Celsius. The corresponding pressure is this, and this pressure is much lower than what the initial pressure is, or in other words, this pressure which is being the initial pressure of the system is much higher than the saturation pressure at 25 degrees Celsius, which essentially means that system is already compressed because the pressure is much higher than the Psat. So this is a compressed liquid. Okay, so what we are going to do is we are going to approximate. Okay, we are going to say that, well, the initial volume, the specific volume is almost same as the saturated fluid or liquid at 25 degree Celsius. So this is the approximation we are going to make use of it, because we don't have question of state at this point, or we don't have any other means to calculate. So we are going to make this kind of approximation, and we will be often making such approximation, okay, for the compressed liquid. Are we going to assign this volume as simply the volume of the fluid at 25 degree Celsius? Okay, so with that we can find out the initial volume V1 as simply V. So this is our specific volume. So this is at 25 degrees Celsius, and this value is here. So we have V1 is 5 kg we know, multiplied by specific liquid, which is 0.001003. Okay, so this is going to be this volume. So what is the total volume here? Total volume of is going to be 2 times the initial volume. So this is your meter cube per kg. So this would be your volume of the system. This we can write as 2 times 0.005. We neglect the other beyond 1, and this would be your 0.01 meter cube. So this is the total tank volume. Okay, so what is the state 2? Okay, the state 2, you already know your V2, the volume of the state 2, and the mass is still fixed. So what is the specific volume for the state 2 is 0.01 meter cube 5 kg. Okay, so this is going to be 0.002 meter cube per kg. Okay, so now we need to find out, we have the specific volume of the state 2, so we need to find out whether it is in a saturated liquid state or vapor state. So again we should check whether this V2 lies in between Vf and Vg, and so we can go back and check our table. The table tells you that Vg is quite large, 43, and V2 is larger than this one. So certainly our V2 is larger than Vf and less than Vg. So this means it's a saturated liquid vapor state mixture, which essentially means that you have, in this process, the state 1, from here the compressed liquid has went to the saturated liquid, and now it has saturated. So this is your Psat, okay, at 25, and now it is in a saturated liquid mixture state. So still P2 is fixed, is Psat at 25 degree Celsius. So still the temperature is fixed because your final temperature is known, 25 degrees Celsius. Considering it's a saturated liquid mixture, the P2 is nothing but Psat, which is given from the table. So this is already given, Psat. Okay, so now I write the energy balance here. Okay, what about the work or any specific energy which is taken out from the system? So what is being provided to you is a Q in. What about E out? So there is no specific work, because when it expands against zero pressure. So you have Q in minus 0, and whatever the change is occurring in the system internal energy, considering the kinetic energy and the potential energy is 0. This can be written as m u2 minus u1. So we are going to approximate again u1, because of the fact that u1 is 1 is in the compressed state. So u1 is approximated as uf at 25 degrees Celsius. Now in order to find out this, that means Q in, because we need to find out the heat transfer. You need to also find out U2. Okay, and you know that U2 is nothing but UF plus X2 UFG. So you need to find out X2. Now this is easy because now you have the information of your volume 2. So X2 is nothing but your V2 minus Vf by Vfg. Okay, so Vfg is known from your table. Okay, so you know your Vfg, Vg minus Vf, and you know your Vf, and as well as you know your V2. So this becomes your 2.3 times 10 to the power minus 5. Okay, so from here you can obtain, now you can plug this in and now use the UF and UFG specific internal energy from the table. Okay, so from there you can obtain the value, and it turns out to be 4.88 kilojoules. So now you can find out Q in, because Q in is now 5 kg, and then you plug in this value. Okay, so 104.88 minus 104.83, and this is of course extremely small. Okay, this is in kilojoules per kg, and this turns out to be 0.25 kilojoules. Okay, so remember that we have considered U1 as U of liquid. Okay, so that was our assumption. This, okay, this was 104.83, and this we calculated based on the quality and the values of the fluid and Fg from the table. So this is the way we solve certain problems based on using the tables. Note that Q in this case is positive, so that means our assumption is correct. We have to provide energy to the system in the form of heat for this particular unrestrained expansion, so such that the temperature at the final state is fixed. So let's end the lecture. In the next lecture we are going to define specific heat at constant volume and other way of or different ways of making use of specific heat for calculating change in internal energy and change in enthalpy. Okay, so see you in the next lecture.